welcome to Mormons, Mystics, and Muons. And today I've got Don Hoffman here. Thanks, Don, for coming on.
Thank you, Gabe, for inviting me. It's a pleasure to be here.
Yeah, I think, I guess first off, I really appreciate not only you coming on, but I feel like you are kind of a gateway for a lot of scientifically or left-brained, logically oriented people to explore things that generally don't fall under those categories. And yeah, I really, I'm fairly new last couple of years in exploring these realms, and I found you as one of the individuals who does a good job of blending both science, spirituality. You have like a really robust framework without invoking anything spiritual or religious of any nature. But I've listened to several of your episodes with Rupert Spear and really enjoyed that you can also, discuss the more spiritual side. So yeah, I really appreciate your work that you've done.
Well, thank you very much, Gabe. Yeah, well, I take both sides with a grain of salt, right? And so, as a scientist, it's my job to understand the theories, but not to believe them, and to push them to their limits and break them, and then try to find new ideas. And that, I think that's the scientific attitude. It's not about believing any theories. It's about understanding the theories and pushing them to the limits and seeing what they can do and admiring what they can do. But then, of course, trying to find out where they break, and they will break, and then trying to get the next thing. And the same thing in spiritual ideas. I think there are many good spiritual ideas out there from various approaches, and I think there's a lot of nonsense as well. And so it's the same grain of salt in both camps, and it's up for each of us to think for ourselves and feel for ourselves and decide for ourselves. We of course, I listen to authorities in both the sciences and spirituality, but I listen to them not to receive the truth, but to get their opinion and then decide for myself. And I think that's a healthy attitude for all of us.
Yeah, I really appreciate it. Before we dive in, I'll let you introduce yourself. I'll give you a little background on me. So I find it helpful. I think whenever I'm listening to a podcast or reading a book or something, it takes me the whole episode to just try to figure out where philosophically or ontologically the other person is. For me, very left-brained, scientifically oriented. I'm a dentist, but my undergrad was in bioinformatics and a minor in computer science. And so always primarily thought that way, but I was raised Mormon. So kind of had this separate part that was also religious, but not very integrated. But I left Mormonism 8 years ago now. I kind of went around in agnosticism, I guess, for a bit. And then only about 2 years ago, when my whole life kind of shifted with divorce and moving and some career shifts, that was kind of the ego death that stimulated me to get into meditation therapy and went through. Are you familiar at all with the Hindu concept of Kundalini awakening?
A little bit, but I'm certainly no expert.
Yeah, and me neither. I just ended up going through having endogenous kind of psychedelic or altered states of consciousness, not seeing anything that wasn't there, but more just like hyper realistic, beautiful colors, bliss states. As I explored all these things, and so that kind of rocked my scientific logical world. Now I experienced this other, and then I was like, well, how do I make these two sides meet together? And
I get emails quite a bit from people who have that same kind of dual experience. It's not unusual. Yeah.
And there's a lot of, I guess my what I feel called to or passionate about is helping, after taking that difficult journey, integrating, and luckily I knew enough about the sciences to be able to find a way back, and integrate the two.
Hmm.
Um, but I see a lot of stories, especially through Mormonism, interestingly enough, because there's a lot of esoteric origins, or parts of Mormonism. So there's a lot of these kind of New Age, um, concepts that bubble up, and many don't integrate it well, and you can see getting off into the weeds and some very difficult, not the healthiest integration. So that's kind of been my journey. I came by way of, I think, Bernardo Kastrup, even though I didn't know about him, but kind of the idea of stacked dreams and the more Tibetan Buddhist idea. And then it was interesting to hear his work. I was like, oh, that's kind of how I philosophically put things together. But was introduced to your, TED Talk, and then I haven't read your book, but I've listened to several of your podcasts. But yeah,
I love
so
Bernardo. He and I are good
pretty in
friends.
line. Yeah. I've enjoyed listening to his work, and listening to Essentia's, watching Essentia's videos. So
Yeah,
that's
yeah.
kind
If
of,
I can get him,
pretty.
yeah, I want him to collaborate with me on some of the technical work if I can get him to do that. But he's still focused right now on the philosophy. So, but he has
Mm,
the mathematical chops to do real technical work. And my own take is that of course the philosophy that he's doing is brilliant and necessary, but to really move the needle in terms of the science, we need mathematically precise theories that make new testable predictions that we go out and
mm,
test, and that's where we'll get scientists on board. I mean, of course, the philosophy has to be done, but it won't move the scientists, and I know Bernardo knows that,
mm.
and it is
Yeah,
important
I guess.
to have, a philosophical a statement of these ideas. Analytical idealism is a brilliant statement of these ideas, and so, but at some point, I'm hoping that he'll join us in really pushing the mathematical frontiers. He has a background in particle physics. I mean, he worked, I believe, at
Mm,
CERN, and I think if we can make predictions that are testable at colliders that come from a realm of consciousness beyond space-time that's mathematically precisely specified, and we're making, you know, 8 decimal places predictions, then people, I mean, it doesn't mean that we're right, but it does mean that at least the ideas need to be taken seriously and given the normal grain of salt that we give in science.
yeah, I guess. Um, that's one question. Like the alternative, I read a fair amount of work and theories, and on quantum physics, and it's fascinating, I think the 2023 Nobel Prize on reality being non-local and non-real. And
No,
I wonder,
22.
like, 22, um, like how many of these physicists have done psychedelics, or like have any experience with altered states of consciousness, whether it's psychedelic endogenous or exogenous. Like that's the other alternative, that it seems like if people that were really hung up on these paradox experience things. I don't know. What are your thoughts on, would that move the needle at all, from logicking things out to experiencing the paradoxes?
Well, I think that there have been a lot of individuals in physics who have had um, those kinds of experiences, and it's affected how they think about, for example, quantum theory. There's a book called How the Hippies Save Physics, I think, which goes into this kind of thing a bit. So there's a whole book
Mm-hmm.
about that, and how that kind of thing sort of flipped. See, quantum theory early on, the founders of it were really thinking deeply about the implications of quantum theory. I mean, it's the mathematics is suggesting some very, very counterintuitive things about the nature of reality, and so Einstein and Schrodinger and a lot of the early thinkers were thinking about what this might mean out of the box. Of course, Einstein was sort of against quantum mechanics, but
Mm-hmm.
so he was trying to show that 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 there was something missing with quantum mechanics. It wasn't foundational, but Schrodinger and others we're thinking about consciousness and how it might be related to quantum theory. Uh, with World War II, it switched. Um, that whole approach sort of died because we had to use it in the war. And
Mhm.
so there came up the shut up and calculate kind of attitude. Don't worry about all that stuff. Just, we built bombs, we built other technology from quantum theory. But then with the hippie movement and some of the the really the bright people doing quantum mechanics, but with that kind of background,
Mhm.
then it started going back to what were those old guys talking about? They were talking about all this weird stuff. Maybe we need to get thinking about the foundations of the theory again. So that's been going on, and it's good because when we actually start looking at local realism, our intuition that space-time is fundamental, and that particles in space-time, electrons, for example, have real values of their properties like position, momentum, and spin, even when they're not observed. I mean, that seems like, of course, but when quantum theory, at least in some natural interpretations of quantum theory, says local realism is false. I mean, people can debate. Some will say, for example, that it doesn't entail that you can get around that with, uh, for example, superdeterminism and so forth. But I think the standard view in quantum theory is that it pretty clearly entails that local realism is false, and non-contextual realism is false, and when Aspect and Clauser and Zeilinger, those are the three guys that won the Nobel Prize in 2022 for their empirical tests of those predictions of quantum theory, and when for decades, and they closed loophole after loophole because this is such a big one that when Clauser does first experiment, people go, yeah, but then there's all these buts, and so then you know uh, so all the buts are Aspect then closed a few more of them, and then Zeilinger closed even more of them. And at some point, people will throw up their hands and say, "Okay, this looks real. It may not be the final answer, but hey, this passes the muster in terms of we've given it some rigorous tests. Maybe we'll find something down the road that makes us rethink this. But right now, it looks like wow, we've tested all the natural options, and so they got the Nobel Prize for it. So the idea right now is the idea that an electron has a position when it's not observed is just plain false. It's just and if it doesn't have a position, if something doesn't have a position, it's not there.
Yeah.
Right? If you don't have a position, you're not there. In a
It's
literal sense, you're not there.
it's interesting because the there's definitely something that triggers people um, in terms of like evoking quantum physics with um, philosophy, but certainly anything spiritual, and or connecting quantum physics with Eastern philosophy. But the original, and I'm not an expert on the history of quantum physics, but it seems like several of the original like founding fathers were very philosophical or idealist in their perspectives, or Schrodinger seemed to be very much about connecting Eastern philosophy and quantum physics. But it seems like there is a something that triggers. I've listened to I watched some episode of Neil deGrasse Tyson talking about and as soon as they talk about quantum physics, they spend a whole little bit kind of mocking the new age sort of perspective of affecting the observer effect. And but yeah, it's interesting that there is such a significant pushback, and sometimes it seems like it's so strong to any kind of overcome the fact that there is this big question mark. There is something to that, and it's uncomfortable to have your whole paradigm model of reality shaken, and so it's easier to attack the idea that that's true.
Yeah, my attitude is pushback is welcome. I mean, if people disagree with me, that's perfect. That's what you want in the sciences. And if Neil deGrasse Tyson is a brilliant guy, so I welcome brilliant pushback. And
Mhm.
you learn from people who push back, and I think that even those quantum physicists who were motivated in part by spiritual ideas would certainly recognize that, of course, the spiritual traditions are not mathematically precise. So it's a matter of a lot of intuition about imprecise words. We're not talking equations here. We're talking just natural language. Natural language is imprecise. So you can get your intuitions and get your ideas wherever you need them, from a glass of beer, from the scripture, from a dream, wherever. But when the push comes to shove, you got to put it into precise mathematics and make it testable. And most of our ideas are just plain wrong. I mean, so I just go into it assuming that most of my ideas, and every once in a while I get surprised. Maybe this one isn't flat out wrong. And so there's a certain humility that's required when you do your science. There's a certain chutzpah. You have to be bold and go out there and try new ideas, but you also have to be completely ready to have your ideas shot down. And so you can be motivated by spiritual traditions. That's perfectly fine. But in the scientific realm, ultimately, it doesn't matter what your motivations were. What are your equations? What do they predict? What are the tests? And do they pass? It's so there's no room for nonsense, but there's plenty of room for inspiration from wherever you can get it. But once you got the inspiration, then you got to turn it into something rigorous. And so that's what I love
Mhm.
about science. It doesn't matter where you get your inspiration. All that matters is what's the final product. Is it testable? Is it precise? Is it compatible with all the experiments we've done so far? If not, doesn't matter where you got your inspiration. This is wrong.
Mhm.
So
Yeah.
sort of a hard-nosed attitude toward the whole thing, but it's hard-nosed in a way that says, but I'm open to any even mystical background ideas that may be helpful to me. Now,
Mhm.
someone like Neil might also be. There are people who will take current science and claim that it says certain things that or about spirituality and so forth that maybe it doesn't, right? It's important to distinguish what the mathematics itself is saying versus here's my interpretation, here's how I would like to think about it. And so when you go beyond what the standard scientific interpretation is, then you need to say, look, this is not what standard scientists are saying about this is my interpretation. And it's right then for Neil to and others to push back on quantum this, quantum that, in context where it's science has not, until the science goes there. We can't say this is what the science is saying right now, and so I
Mhm.
think pushback on that is important.
Yeah. Yeah. I think what bothers me, what I guess what triggers me sometimes is the pushback without any logic behind it, but just like, oh, this idea is ridiculous. But yeah, I think
Right, right.
I'd agree with you. Why don't you give us a little introduction of your background, and then kind of walk us through the Cliff Notes version of interface theory of perception, and that'd be fun to. And I'll link to your TED Talk and probably your Lex Friedman podcast is kind of like a shorter or longer version. And then I've got some questions on kind of diving deeper from there.
Okay, yeah. On the interface theory of perception, I was very interested in science and spirituality as a teenager because my background, my father was for a while a minister in the Protestant fundamentalist sect, and so I was in church services all the time, and so I got that point of view quite well, and I read the Bible cover to cover. And then, in school, I was getting science that seemed to contradict some of the things I was hearing in the church, and so I was very interested in that. And then I ran across some Christian thinkers who were actually quite intellectually stimulating, like C.S. Lewis. And so I started reading C.S. Lewis and a guy named Francis Schaeffer, and I realized that I could try to think about these issues in a more philosophically sophisticated and even a scientific kind of way. And so I fashioned for myself the question, are we just machines? That's how I finally sort of shaped it for myself. I mean, it seemed like on the science side, I was being told I'm pretty much a machine. And on the spiritual side, I was being told I'm not a machine, but 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 science was delivering the goods, right? All the technology was from the science. None of it was coming from the spirituality, and there were things in the spirituality that were obvious nonsense to me. So it became very, very strange. It also didn't seem right that I was just a machine. But if science is delivering and it's doing all this stuff and it says I'm a machine, I can't just dismiss that out of hand. So it's an interesting thing. As a teenager, you go, okay, I'm getting all the experts. I mean, I'm just a little kid. All the experts are telling me contradictory stuff, and there's something that seems wrong on both sides, and something that seems perhaps right on both sides. So it looks like I'll have to figure this out for myself. uh, and so the question I finally posed was, are we just machines? And so I got an undergraduate degree. My bachelor's was from UCLA in quantitative psychology. So it was like a minor in mathematics and computer science and a major in psychology, because I was trying to, what are humans and what are machines? And then I went to MIT, again with the dual focus. I was in the artificial intelligence lab at MIT and what's now the brain and cognitive science department. Again, trying to study what's humans and what can machines do, what's neuroscience and of human intelligence and so forth. And you have to pick a particular. You can't just talk about, like, in general, are we just machines? You need to pick a problem to do a PhD. So I worked in visual perception. My advisor was David Marr and Whitman Richards, both wonderful, wonderful, brilliant men. And I worked on visual perception, and I did some work on how we recognize objects. So I was looking at visual perception as sort of the door, right? I had to do something concrete. Can I understand how visual perception works in a mathematically precise way? So I was actually writing Lisp programs to implement my ideas and see what happened. We had these wonderful little Lisp machines back then at the MIT AI lab. And but I noticed that a lot of my fellow graduate students and professors there at MIT were working on visual perception and perception more generally. And we were coming up with mathematical models for specific things. How do we see depth? How do we recognize objects? How do we see shapes? How do we interpret colors and so forth? And I began to see, as I did my own research and listened to the research of others at MIT and elsewhere, that there were some common mathematical structures to the theories of perception that were coming out. And I thought, well, that's really interesting, because ultimately we would like a deep theory of perception more generally, not just of this perception and that perception, but could we get a mathematical theory of perception? And so I wrote a paper, a position paper, and gave it to my advisor, and David Marr, and he looked at it, and I had this general mathematical theory, but it was, I'm not a mathematician, and all I knew about was Euclidean spaces. And so he asked me, so why are these various spaces just Euclidean spaces? And the true answer was, well, David, because that's all the mathematics I know. And so he said, but there's no good reason for these things to be Euclidean spaces. So I shelved it. I said, okay, I'll just do my specific work on object recognition and 3D shape from motion is what I did my PhD on. Then I came to UCI as a professor in 1983, and I hooked up with a mathematician at UCI named Bruce Bennett, a brilliant, brilliant mathematician. And after I got to know him for a few months, I pulled out my paper and said, Bruce, here's my idea about a general theory of perception. And Bruce looked at it, and he said exactly the same thing that my advisor said. He said, Don, very interesting, but why in the world are you saying these things should be Euclidean spaces? And I said, Bruce, because that's all the mathematics I know. And he said, oh, okay, well, I said, so what do we need to do? And he said, well, make them measurable spaces. So in a few minutes, I knew what measurable spaces were, and we were off to the races. So it wasn't a big deal. Of course, there was a lot of math that I had to learn. Measure theory is not trivial. But so then that's what got me going, was I finally had a collaborator who could teach me the math that I didn't know and was very, very patient. Bruce was extremely patient with me. Um, we worked from 1983 until he died in 2001 or 2002. He he taught me a lot of math, and for which I'm very, very grateful. And we worked together and collaborated and developed a theory of observation. We published a book called Observer Mechanics. So came out in 1989. It was really a theory of consciousness, but back in the 80s, you couldn't talk about consciousness. It wasn't respectable, so we just called it observer mechanics, a formal theory of perception. But but it really was a theory of perception, but really a theory of consciousness, in which perception was fundamental, not the physical world. And so it was that theory, developing that theory, that made me begin to think that maybe space and time and objects in space and time aren't fundamental. That it couldn't prove it, but it certainly, now it seemed like that was an option that was on the table, and our theory seemed to be supporting that point of view. And so I thought about that quite a bit, and did you have to do your regular work and publish papers and so forth as a professor, and move up the ranks. But I was always thinking about that, and finally, in about 2005 or 2006, I thought, maybe the tools of evolution would really help to answer this question: is is space and time the truth, and objects in space and time, are we seeing the truth or not? What if evolution said that there's a low probability that we see the truth? That would really be a game changer here. And there was some work. I mean, Steven Pinker, in his book How the Mind Works in 1998 or 1999, already had given lots of important examples about where our cognition and perception, um, and evolutionary psychologists more generally, not just Pinker, but Pinker was a brilliant thinker, and really gave good statement to these ideas, that there are selection pressures to have false beliefs and false perceptions. We have heuristics and biases. We have shortcuts. We have to do things quickly, and we also try to impress people with and so there's all sorts of reasons why we might not see the truth or believe the truth. But even those thinkers still assumed that there's a limit to that for everyday middle-sized objects, tables and chairs, forks and spoons, we're not getting exhaustive truth, but what we're getting is true. And it's there really are things like forks inside space and time, and spoons and tables and chairs, and we may get shapes and so forth a little bit off, but they really do exist. And so I thought, well, what about that one? I mean, does evolutionary theory, what would evolutionary theory say? And I thought, my own thought was, there might be selection pressures to not see the truth even in those things, just because it limits in time and computational resources. It takes a lot of time and computational resources to compute things accurately. So I thought maybe that might. But in any good science, what you have to do is jump in, do the math. So I got some graduate students working with me, Brian Marion and Justin Mark and others. We all learned some new mathematics, evolutionary game theory. So we got a book called Evolutionary Dynamics, a wonderful book that came out in 2005 or 2006. So we were grateful that someone actually made the mathematics accessible to people who weren't in that field. So we learned enough math to actually run some simulations. And in the process of doing that, I began to realize, what I thought was fine, there are selection pressures for doing things quickly and cheaply, and those tend to go against seeing the truth exhaustively. But that wasn't the real story. The real story came out, and it was Brian Marion who pointed out to me as we were doing this, that the payoff functions, it was the payoff functions, and I'll talk about what a payoff function is in evolutionary theory, but the payoff functions are sort of the thing that controls the whole game in evolution. So, and the payoff functions might not have information about objective reality. They might not be, in some sense, what we call homomorphisms of structures in objective reality. And Brian pointed out that in the simulations we were doing, it was when they weren't homomorphisms that we were getting these results that that the simulated organisms that we had weren't saying the truth anymore. And so I've been okay. So the payoff functions, and are the payoff functions homomorphisms of objective reality? So what's a payoff function? It's in evolutionary in evolution. You can think about life as a game, and like a video game. And in video game, you have to get a lot of points. And if you get enough points, you can get to the next level. And if you don't get enough points, you die. Okay, sort of like that in evolutionary theory. Um, the points are payoffs, and if you get enough payoffs, you don't go to the next level, but your genes do. Your kids, you have kids, and they go to the next level. So it's about reproduction. So these payoff functions um, are functions from the world. So whatever the world is, and your state, your action, you get payoffs, right? If I'm in Grand Theft Auto and I driving my virtual car and I decide to run into a brick wall, well, that's bad for my function in the game. I have bad payoffs, right? So you don't want to do that in Grand Theft Auto. Don't run into brick walls. Well, the same thing in evolutionary theory, right? If I'm an organism and I'm hungry and I'm looking to eat, well, if you're a human, don't eat poison ivy. That's a really bad idea to eat poison ivy. So there are going to be payoffs. Here you take an organism, its state, and its action, like dawn, hungry, and wanting to eat, and then you say for different actions you could take, what are the payoffs? Well, if you eat an egg, that's pretty good. That's healthy for you. If you eat a piece of cake, well, so. And if you eat poison ivy, you're dead. That kind of thing. So you get different payoffs. And so the question then came, okay, what is the probability that a randomly chosen fitness payoff has any information about the truth of the world, the true structure of the world? Technically, it's what is the probability that a payoff function will be homomorphic to any structure of like to be, just for those who are interested in a little bit more technical structures like a topology, a metric, a measure, or whatever it might be. So there's lots, a total order, partial order. There's lots of structures that the world might have, and you can ask in each case, what is the probability that the payoff function, that a randomly chosen payoff function would preserve that information? Because if it doesn't preserve that information, there's no way it can shape you to see that information, right? It can't tell you to see what it doesn't know about. So that was the real. And so I worked with a mathematician, Chetan Prakash, who's worked with me almost as long as Bruce did. He came in 1984, 1985. Bruce introduced me to Chetan, and Chetan and I still collaborate to this day. So without Chetan, I would have almost nothing. Chetan is the brilliant mathematician I've been working with, and so gave this to Chetan. We did simulations which showed in the simulations, and we did publish this in the Journal of Theoretical Biology, which is a good journal. We published our simulations showing that in the simulations we did, the simulated organisms that saw reality were dying when they competed against organisms that saw none of reality and were just tuned to the fitness payoff functions. But simulations are simulations, theorems are theorems, and so the simulations were enough to say, okay, this is worth asking Chetan. Let's. So I proposed some theorems, and then Chetan, of course, took them to the next level, and proved that generically chosen fitness payoff functions simply won't be. We did it for several different specific structures, but the lesson is quite clear. Pick any structure you want, and then look at the set of all homomorphisms from that structure into a set of payoffs. Like maybe payoff values might be from 0 to 100, right? 0 means really bad payoff. It's going to kill you. 100 means perfect payoff. You're going to have thousands of kids. This is that. So there's a difference. That's what payoff values are. Look at all these payoff functions, and ask how many of them. You can literally count how many of them are homomorphisms of a measurable structure or a total order or a partial order, whatever it might be, or metric. So you can just count them and then take the limit. What's the total number of payoff functions? And then the total number, so you put the total number of payoff functions in the denominator, and in the numerator of a fraction, you put how many of them preserve structure of reality. And then you just increase the range of functions, the resolution, so the number of functions goes up and up until you go to infinity. You ask in the limit, as the number of functions goes to infinity, what fraction of them have information about a reality? And the answer is zero. And not approximately zero, exactly zero, precisely zero. So there's a 0% probability. Now, that any organism has ever been shaped by natural selection to have any sensory systems that show it any aspect of objective reality whatsoever, zero. So it's a stunning theorem. Now, one can say, well, why should you choose them at random? Certainly, maybe some payoff functions are more probable than others. Maybe so. Current evolutionary theory gives us no theoretical grounds for picking one payoff function over another. Now, I'm not saying that someone couldn't change evolutionary theory and say, okay, the set of payoff functions really needs to be biased towards ones that will help us to see the truth. Great. Write down that evolutionary theory. That's not our current evolution by natural selection theory. There's nothing that says here's the proper measure on the set of payoff functions. They're all equally likely, and there's no rule in current evolutionary theory that says you have to pick the ones that will make you see the truth. Doesn't say that at all. But I'm not doctrinaire. If someone wants to go after that, absolutely, give it your best shot. Write down a new version of evolutionary theory that says here's why you can't have an unbiased, sort of like what you might call a Lebesgue measure. In technical terms, a Lebesgue measure on the set of possible payoff functions. You need to have a biased measure, one that's biased towards these payoff functions that will let us see the truth. Perfectly fine to try to write down a principled new version of Darwin's theory, a new version of evolutionary game theory that has that bias. But that's not the current. So our current theory of evolution has this clean implication. The probability is precisely zero, that anything that you see, hear, smell, or touch or taste in any way resembles whatever objective reality might be. So that's now that's the mathematical result. Now I should say, perhaps the most, of course, I've gotten a lot of pushback on this, right? Because the implications of this are revolutionary. It's completely revolutionary. So I've gotten lots of interesting pushback from very bright people. From philosophers, here's the kind of pushback that I typically get. They'll say Hoffman has shot himself in the foot logically. That he's actually, as one philosopher put it, in an unfortunate dialectical position. And here's the argument. Hoffman is using the mathematics of evolutionary game theory to show that certain key concepts of evolution, or Darwin's theory of evolution, namely physical organisms in space and time competing for physical resources like food and mates, that those physical objects are illusions. So Hoffman's got a real problem. Either the mathematics of evolutionary game theory faithfully models Darwin's ideas, or it doesn't. Now, if it doesn't, he couldn't possibly use it to contradict Darwin's claims about physical organisms in space and time being real. And if it does model Darwin's ideas faithfully, then it wouldn't contradict him. The mathematics that if it faithfully modeled Darwin, it wouldn't contradict his fundamental ideas in his theory. So in either case, Hoffman is in a logical bind and he shot himself in the foot. We don't need to look into the details of his theorems and so forth. We know that somewhere, somehow, Hoffman has shot himself in the foot logically, and it's his job to find out where he's gone wrong. It's not our job. We're not interested in that. Okay, so it's the self-refutation kind of thing. And at first blush, this sounds like a pretty good argument, but what it misses is the basic method by which science advances, and also what is a scientific theory. So first, what is a scientific theory? It's a theory says, grant me these assumptions, and if you grant me these assumptions, I'll explain all this other stuff. So every theory makes certain assumptions. Those are the premises of the theory. And it says, if you grant me those premises, those assumptions, then I'll explain all this. So Einstein, for example, grant me that the speed of light is the same for all observers, and grant me that the laws of physics are the same in all inertial frames. And he gives us special relativity, which has been transformative. And you grant me that E equals h nu, energy equals Planck's constant times the frequency, is the energy of a quanta of light, for example, and I can explain the photoelectric effect. So that then Einstein gives us a beautiful theory of light and a beautiful theory of space-time and so forth. And then general relativity as well, same kind of thing. Now, here's the point. Every theory has its premises, and then it leads to the things that it can explain. But there is no theory of everything, because you don't explain your assumptions, you assume them. You're not explaining them, you're assuming them. That's what assumptions are. Things that are, my assumptions are the things I assume, and I'm not going to explain. These are my miracles. These are the miracles of my theory. And when you, as a scientist, what you do is you make your assumptions mathematically precise. So Einstein, for example, in his general theory of relativity, I think in around 1906, 1907, he had the big idea for general relativity. If I'm standing on a weighing scale in an elevator and someone cuts the cord of the elevator and I'm all of a sudden in free fall, all of a sudden my weight on the scale in the elevator would be zero. All of a sudden I would be weightless. That was his big idea. Then it took him several years, I think 7 or 8 years. And he was Einstein, right? So this is no slouch. It took him 7 or 8 years to turn the idea into mathematics. And that's the hard part of science, right? You can have your ideas, and ideas are not a dime a dozen, and Einstein's idea was extremely valuable, but you have to take the next step and turn it into mathematics. So Einstein took his own idea, struggled and turned it into mathematics, and in, I think, 1915, published the general theory of relativity. So he himself had taken his ideas about space-time and made them mathematically precise. Now, the thing about scientific theories is, because they make assumptions, they don't explain everything, period. They don't explain their assumptions. That means there is no theory of everything, period. Science will never have a theory of everything, because it's in the nature of theories that they must make assumptions, and those are the miracles of the theory. And that means that every theory must, by its nature, have its own scope and its own limits, period. There are no exceptions to that. There are no theories that are the theory of everything. So the only question is the mathematical formulation of your theory good enough to show you both the scope and the limits of your theory? It will have limits. There will be a place where your theory breaks. Is the mathematical formulation of your theory precise enough to show you what your theory can do, and also where your theory will break? And this is true. This is going to be true of any genuine scientific theory, not just Hoffman's theory, or any theory will necessarily have its limits. And a good mathematical statement of the theory will tell you where that theory stops. So in Einstein's case, his mathematics, he didn't understand this when he wrote it down, but within a year or two, a German scientist, actually on the front lines apparently in World War I, was working with Einstein's equations. So hats off to someone who can actually do math in the front lines. I don't know how you could do that, but he found one implication of Einstein's equations: black holes, places where space-time ceases to work. And further work has shown that the very notion of space-time, using Einstein's own mathematics as a critical part of this, you find that space-time, which was the idea that Einstein himself mathematized, falls apart at 10 to the minus 33 centimeters and 10 to the minus 43 seconds. We use Einstein's own math together with his equation E equals h nu, and some insights from quantum theory to mathematically show that the notion of space-time has a scope, a wonderful scope, and a limit. It ceases to have any operational meaning at 10 to the minus 33 centimeters and 10 to the minus 43 seconds. Now, we don't go back, we can try to pose the same thing to Einstein and so forth. Well, so either Einstein's equations faithfully represented his ideas that space-time is fundamental, or they didn't. And if they didn't, then you couldn't use them to show that space-time isn't fundamental. And if they do faithfully represent Einstein's ideas, then they couldn't possibly show that space-time isn't fundamental. Well, you've got the science wrong when you say that. His own equations are an integral part of the discovery that space-time, the very concept of space-time, has certain limits. And that's not the exception, that's the rule. That's the way science works. So it's not an unfortunate dialectical situation that I can use the mathematics of evolutionary game theory to show the limits of certain concepts in evolution, namely physical objects inside space and time. That's the sine qua non for good science. So what the philosophers are taking as an unfortunate dialectical problem, Hoffman shot himself in the foot. No. That's the way science works. What's unfortunate is misunderstanding the relationship of our mathematical theories to the ideas in scientific theories. So that's perhaps the one of the most interesting kinds of pushbacks on this. Another pushback I've gotten is from my colleagues in cognitive science, where they're trying to say that, so there's a group, and I'm not mentioning names because I'm disagreeing with them, so I'm not going to try to pillory people or anything like that. So this is not, so I'll make absolutely sure that it's not personal by just making it not personal, not mentioning names. There's another group, and people who are interested, you can go find the papers. They're published. They argue that not that I've logically shot myself in the foot, but that the idea that evolution shapes us not to see the truth is missing some technical things. So they'll argue. One group has argued, and this gets a little technical. They argue that there's no cognitive penetration of perception. So that's the first step. So what that means is we have certain cognitive beliefs about our world. I believe the sun will rise tomorrow. I believe the earth is round. I have all these different kind of beliefs. Mm-hmm. And the question is, what is the probability that our higher level cognitive beliefs could actually affect the details of our perceptions? Could my beliefs actually get in there and affect how I see things at a perceptual level, not a conceptual, but at a perceptual level? And there's been a debate in the philosophy of science and cognition. Fodor and has debated with Paul Churchland. I think the early '80s. Well, Fodor argued there is no cognitive penetration of perception because, and there better not be, because as scientists, we want to use the data from our senses to test our theories. And if the theories that we believe could actually affect the data that we perceive, that would really shoot science in the foot badly, right? And Churchland said, but we have every reason to believe on clear studies of cognitive science that our perceptual systems themselves are riddled through with various kinds of assumptions and beliefs. Maybe not top level cognitive beliefs, but beliefs. So there's been a back and forth, and about that, and so this one group said, let's assume that there is no cognitive penetration of perception. Okay, that's perfectly fine. I'm happy to accept that for sake of argument. Then they said that that entails that there's only one map from the world to a particular sensory experience. There's only one map from the world to a perception, and that turns out to be false. It doesn't follow that cognitive penetration, that there is no cognitive penetration of perception doesn't mean that there is only one map from the external world into our perceptions. There's multiple streams of visual processing. There's a dorsal and ventral stream. There's in fact multiple senses with multiple. If you see what we call a rock, you can see it with your eyes. You can touch it with your hands, and you can hear it clank against another rock with your ears. I mean, there's all sorts of maps from one object in external world, if I'm using the physicalist framework, to our experiences. So they make this strange claim, but wave my hand. I'll go ahead and grant it. Then they say that then, but there could be many different payoffs. So if there's only one map from the external world into your perceptions, but there could be many payoffs that are affecting you. Then they argue, and they do simulations that if you have thousands and thousands of payoffs, and you throw them at a person really quickly, and you force them to only make one map, then effectively you ignore all the different payoffs because the payoffs are changing radically, and you just look at the truth. So in some sense, what they're arguing is um, payoff functions, which are the key notion inside evolution. What you do is you throw them so fast and furious that no particular payoff function is in fact relevant, so that you can't be tuned to the payoff functions, and so you're only tuned to the truth. So that's and so they show that in their simulations. And so we're working on a reply right now to reply to that. But one answer is basically first, even if you have many payoff functions, you're not required to only have one map. And what if you do what we call cluster analysis? I can take a bunch of payoff functions that have a similar payoff structure, and I can start to cluster my functions so that I actually get, maybe I have 1,000 payoff functions, but these 200 payoff functions have maybe they have a roughly Gaussian structure, so I can group them together. And these have some kind of other structure, and I can group them together. And then what I can do is have 3 or 4 maps, or 5 or 6, or dozens of maps, that each one though is looking at a different set of payoff functions clustered. And what we show, and we've done the simulations, so it's just a matter of writing the paper up. And when we do the simulations and do this cluster analysis, then their argument goes away. We then show that you're shaped to actually be tuned to the payoff functions, which means you're not tuned to the truth, because almost every payoff function is not the truth. It's not homomorphic. And so what we find is that, in fact, the probability that you see reality as it is again, minuscule. So you can see that, by the way, I'm not complaining about this pushback. This is exactly what is supposed to be done, right? We're supposed, and by having the philosophers push back, it forces me to point out this important aspect about the nature of scientific theories, that every theory has its endogenous limits, and the mathematics better show you the scope and the limits of that theory. It's not a trivial point. And then the work of the cognitive scientists that I was just talking about, that pushback is welcome. It's forcing us to say, look, there's this aspect that we didn't discussed in our earlier papers in terms of the details of this implementation about clustering the payoff functions into groups. And my own view is that I can see a human can see 30 or 40,000 fundamentally different kinds of objects, basic level objects in nature, tables, chairs, forks, spoons, and so forth. There's roughly 30,000 objects that we can perceive. My take is that each one of them is a cluster, a cluster of payoffs that we've sort of put together into what we call an object. So what we call a physical object is nothing but one of these clusters of payoff functions, and we have thousands and thousands of these, and they're not the truth. They're just convenient representations of the payoffs. So ultimately, the pushback is fine because it's going to, I mean, we have to reply, we have to do a paper on it, and is forcing us to then show the next step in this theory. So that's sort of the big idea. But I'll just step back and say what the big picture here is. And the big picture is we naturally assume that we see. I look at a table, and on the table there's a fork and a spoon, and I say to you, do you see a fork and a spoon? And you say yes, and I assume that we're both looking at exactly the same real physical object, and that fork and that spoon would be there even if no one looked. I'm assuming that space and time and physical objects are real, and they exist even if no one perceives them. And what I'm saying is our best theory of evolution, our current theory of evolution, says the probability that we're seeing the truth is zero. The probability that space and time are fundamental and that objects in space and time are fundamental reality is precisely zero. And that is a true shock to the system. And I'll just finish by saying, remarkably, physics, independent of evolution, is saying the same thing. Einstein's theory, as I mentioned, is saying that space-time ceases to have any operational meaning at 10 to the minus 33 centimeters and 10 to the minus 43 seconds. It's a very shallow data structure. It falls apart at 10 to the minus 33 centimeters, not 10 to the minus 33 trillion centimeters, just 10 to the minus 33. So it's a cheap data structure. It's not the truth. And that's the implication of Einstein's theories of space-time together with quantum theory. So we have our two pillars of modern science: evolution by natural selection, and Einstein's theory of space-time together with quantum theory, so quantum field theory and general relativity. Those are the pillars of modern science, and those pillars are unanimous in saying that space-time and objects in space and time are not fundamental reality. They don't tell us what is fundamental reality. No surprise, right? Every theory has its scope and its limits, and it can't tell you what's beyond those limits. By definition, it can't tell you what's beyond those limits. Those are its limits. What you can do as a scientist is to say, okay, first, time to party and celebrate because we found the limits of our current theories, right? It's wonderful because we know that there are limits. The only question is, are we smart enough to know the limits? It's not a question of whether there are the limits to the theory. And that includes my theories. My theories will have their limits. They're not the final word. So the only question is, have we been smart enough? And has our mathematical formulation of the theory been detailed enough to allow us to find the limits of that theory? And when we have, that's time to celebrate and then to make bold moves. Okay, what new, deeper assumptions will allow us to go beyond the limits of space-time, for example? What kinds of objects, what kinds of entities can we postulate outside of space-time for the next step in science? And then whatever new theory we come up with, we're going to then have to project it back into space-time. So we have to have a map from our new theory into space-time and where we can test it, right? Because right now we only have all of our experimental apparatuses are things inside space-time. That's all we know about how to do right now. So that's where we can test it. So so it's not that anything goes, whatever, get your ideas wherever you can. but eventually you're going to have to take those ideas, project them into space-time. First test will be, in space-time, do they agree with Einstein, and do they agree with evolution by natural selection inside space-time? They better, or you better have good, tough reasons why there's some difference between your projection and what we knew and thought about from Einstein's theory and evolution. And they better be testable, and you better win in the experimental tests over the old theories. Otherwise, we have no interest in what your ideas outside space-time are. So it's not that anything goes. No, the current theories will give you a first thumbs up or thumbs down on your new theory. And then the experimental tests will really give you a thumbs up or thumbs down. And a thumbs up doesn't mean you found the truth. It means you found a good next baby step in the scientific exploration. That's all a theory is the next baby step. It can never be, and my own view is that even if we could do science for the next billion years, and we had 10,000 Einsteins in that time, we would barely have scratched the surface of reality. In other words, the relationship between reality and scientific theories is infinite to one. And yet, you might say, well, then if you think that, Hoffman, then why do science at all? I think that science gives us useful theories of projections of reality. Reality is whatever it is.
Mm-hmm.
Reality is whatever it is, and scientific theories are descriptions not of reality as it is, but of a projection of reality. And most of our ideas are just nonsense. Most stuff that we come up with, every once in a while you have a Newton, an Einstein, a Schrodinger, a Heisenberg. Every once in a while. Most of the time, most of the stuff we come up with is not only not the truth about objective reality, it's not even close to a good description of our little projection of objective reality. So most stuff is just off the table. It's just not interesting. Every once in a while, you get something that's a good description of our projection. So science is wonderful for that.
Yeah, it seems like some of the particular things that what you're talking about bring to mind is the need to be construct aware. Everything that we discuss, and space, time, idea of separateness, other people, what we call God. I mean, they're all meaningless in the sense that they're just constructs that we've made up. They're meaningful in as much as they allow us to create some predictive model of what's going on and to share and discuss that with other people. But yeah, if we're not aware, if we get too attached with the label and the construct as being a fundamental truth rather than a placeholder for whatever that really is that we recognize that we may not fully understand, then we get stuck because we get attached to, oh, this is truth, rather than this works for me now, this helps me predict things. And then once I get more input in where my model breaks from within, then I've got to update my model into something that now helps me predict these new outliers.
I completely agree. And science and spirituality have both been approaches toward trying to describe reality in a way, right? The spiritual traditions have said we're telling you we're talking about reality, but the good spiritual traditions will say, look, all of our words are just pointers, right? They're not the truth. The Tao Te Ching, the very first line in the Tao Te Ching is the Tao that can be spoken is not the true Tao. In other words, if you can talk about it, that's not it. And if you understand it, then the Tao Te Ching doesn't stop there. It then goes on and talks, right? So it's saying once you understand the nature of language, and once you understand that framework, then it's perfectly fine to use everything else as pointers, not as dogmas, as pointers for you to explore the nature. And the same is true of science. Our scientific theories are not the truth; they're pointers. But the advantage of science is that the pointers the mathematical pointers in science tell you their scope and limits. They actually tell you that, whereas natural language doesn't. And so it's
Mhm.
very easy, even if the originators of a particular spiritual tradition were very, very clear. Don't be dogmatic about what I'm saying. These are just pointers. Please, please don't be dogmatic. Centuries later, their followers are killing each other because you didn't say it exactly. You don't believe in this. Well, then you're a non-believer, and not. And we have a history of millions and millions of people being killed because they mistook pointers for the absolute truth, and they felt it their duty to kill people who don't believe the absolute truth.
It's
So that's where science really
interesting.
gives us. I'm not saying science is the panacea, but in the interaction of science and spirituality that I look forward to, I would say that we could start to get precise pointers in the spiritual realm that are mathematically precise. I think it's some spiritual traditions make a big point that they're saying the same thing they said 3,000 years ago. And from my point of view as a scientist, that's not nothing to boast about. That's sort of like, oh wow, maybe it's time for us to make progress. Those are old pointers. Have we maybe no pointer is the truth. The only question is, have we been able to evolve our pointers as we've evolved spiritually? Can we evolve new pointers that can help us grow spiritually? Being stagnant for 3,000 years is nothing really to boast about. So I, so, and again, maybe many of the old pointers are very useful. Some of them are probably false, I mean, and not useful. But what about having a living, evolving, quote unquote, science of spirituality, where we're developing new pointers, not attached to the pointers, looking at the very limits of those pointers as we develop them, saying, here's the limits of this idea. If you can talk about it, that's not it. We understand. If you can talk about it, ultimately that's not it. But we do need to talk
Mhm.
as pointers. And the notion of pointer here, I think is an important one. I'll just say one other thing about it. How do we learn words? I mean, when you're a little kid, at a certain point, when you're 12 to 15 months of age, and then for months thereafter, you're ready. And what happens? It's you learn by what's called ostensive definition. So mom or dad is there with Junior. Junior's sitting, and there's a rabbit on a mat, in front of Junior, and mom or dad points and says rabbit. And Junior, at the right age, looks and remarkably gets it. Right? You only have to point once or twice, and all of a sudden, kids will get it, and they generalize quite properly, very, very quickly. So what's going on there? That's called ostensive definition, defining by ostent. You point and say the name. Well, if you think about that, you might say, "Duh, that's tell me something interesting, Hoffman." That's of course that's how you learn words. If you think about it a little bit further, you realize it's a miracle. That kid and that parent are doing something that's almost impossible. How, when the parent points and says rabbit, there's a million different things that could have meant. It could have meant the ear of the rabbit. It could have meant the color. It's a white rabbit, not a brown. It could have meant the fur. It's got a furry. It could have meant the left paw and part of the patch of the carpet. It could have meant the left eye of the rabbit and the left foot. There are countless things you could have referred to. How in the world did the mother or the father know what to say, and how did the kid solve that infinite induction problem? It's an incredible. So, and we know, for example, here suppose that there's the rabbit sitting on the mat, and mom points and says quadruped. Now, we know the mom is screwing up the kid. That you don't want to, that's not the first word you're going to teach. It's not quadruped, it's rabbit. And it's not fur. You're not going to say fur, you're not going to say white. You're going to say rabbit. So how does the mom know that? And how does the kid know? So we know the rules of the game, and it's actually funny to us when someone would violate the rules. So, but notice that the mom, in some, or the dad, in some sense, is not teaching the kid anything. They're pointing, they're giving a name to something the kid already has. The kid has something already. The reason they can't get the name until they're 15 months of age is because they didn't have that thing yet. Now they have it. And so now you can point and just give that. So you're not teaching the kid anything except, hey kid, whatever it is that you're seeing and whatever that object is that's important to you, I know what, I have an idea that this is important to you. We call that thing rabbit. That's all mom is doing, right? And the same thing if you've never had cinnamon before, and I say, oh well, let me tell you about cinnamon. Well, I can describe cinnamon till I'm blue in the face. You'll never know what cinnamon. The only way I can do is say, here's a piece of cinnamon, taste it. Then I give you, my ostensive depth. I say, Gabe, that is cinnamon, but you had to taste it yourself. Well, am I teaching you anything? No, you are the one that's creating the cinnamon taste. That's you. And all I'm doing is giving you a trivial thing. We call that, whatever you've just created, Gabe, we call that cinnamon. That's true of all of our words. You live in your world, I live in my world. We exchange labels for things. So I actually, even though we use words the same way, it doesn't mean that your perceptions are any way like mine.
Yeah, which is why it becomes really almost humorous when I hear people arguing about whether God exists or not, because they're both operating under the same assumption that they're talking about the same thing, and they're also operating under this kind of false dichotomy that he either exists as this entity separate from ourselves, even if they're talking about the same narrow definition, or the only other option is that that he doesn't. Yeah, so it's been interesting to kind of circle back and recontextualize some of the Bible stories, because a lot of people, when they leave religion, particularly Mormonism, which is a fairly logical religion in the sense that it does cross a lot of T's and label I's, and that they got kind of a plan for people that didn't hear about Christ in this life. There's it appealed to me, and appeals to a lot of people that like, oh, this is a bit more logical, and I think that owes to its esoteric roots, whether it was psychedelics or whatever else was happening with Joseph Smith at the beginning. But usually when people leave, they kind of swing to the other side, like atheism and materialism. And yeah, so there's this, the term deconstructing is popular, but often I think that deconstruction only goes to a certain point, and they don't get to deconstructing the language and reality and consciousness and whatnot. Because I think that's the most difficult part, is it's not so much the learning, it's the unlearning that allows you to learn and make new models. But the Bible stories that have had more meaning now is, thinking about the creation and the naming of this. Oh, this is really the creation, is us putting names on things and categorizing and clumping so that we can progress forward. And then the Tower of Babel story, which is really fascinating, because these people are trying to get to God, whatever you believe God is, and what becomes their downfall is language, and the confounding of language, in the story, is because they speak different languages, but really just the not being aware of the limits of language and being imprisoned by not realizing their pointers ultimately is what prevents you from grasping God, you know, the universe, whatever the ultimate truth that you're seeking after.
Yeah, there's the issue of language, our conceptual system versus reality, and what is the reality that we tend to be stuck in our thoughts and stuck in our way of conceptualizing reality. But what is the deep nature of reality? Um, and no scientific theory, as I said, can ever be the theory of everything. So certainly no language theory that's even less rigorous than a scientific theory could ever be the theory of everything. So the question then, I think the big question for each person is, who am I? Who
Mhm.
right? If there is no language that completely describes reality, there is no language that completely describes my reality. So what am I? Well, I whatever I want to think about myself, whatever theory I want to say about myself is, as I was saying earlier, 0% of the truth. So that then leads to a more meditative approach to the whole question, which is in meditation where you sit and let go of all thoughts whatsoever. So who am I? So you ask yourself, sit down in a quiet place and ask yourself, who am I? And then don't take that as an invitation to think about who I might be. Take it as an invitation to just be. So let me just be myself without any thoughts, and then go more and more deeply into that 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 can't be described, and have that be so. Instead of having our explorations be limited to thought explorations, have this other avenue of exploration, which is direct awareness without thought, and spend time there. And I think that is so many spiritual traditions have talked about that. They call it meditation and so forth. But and I that's where I often get my scientific ideas, is when I go into I say, of course, on the one hand, I'm going to study these scientific theories. I'm going to learn the mathematics. I'm going to be very, very mathematically precise. And then I'm going to choose at other times to say, how do I get to a new theory? Well, I need to step out of concepts altogether. And that's where the insights come from. But the question then arises, who am I? And our best theories rule out some of the answers that we normally assume are true. I am a little object in space-time, right? There was a Big Bang 13.8 billion years ago, and for who knows how many hundreds of millions of years there was, or billions of years, there was no life, but eventually life somehow evolved, and then eventually that life became conscious, and then after who knows how many more hundreds of millions of years, finally my kind of consciousness evolved. And so I'm a tiny little object in space-time. My consciousness is somehow a product of my neural activity, and it evolved, and that's who I am. Well, that's not who you are. Our best scientific theories tell us that space-time is not fundamental. So space-time itself is just a data structure. So you're not a little object in space-time. In fact, it's the opposite. Space-time is a little theory inside you. So space-time is your little theory. It's your little headset, if you like the virtual reality analogy. It's just a little headset that you are using. It's a way that you're perceiving reality. But you're not the avatar that you see inside the headset. Your body is just an avatar. Space-time isn't fundamental. Your body is a little object in space-time, so that's not fundamental. That's not who you are. So one reason why I'm talking about this stuff is it might seem like, oh, this is all airy-fairy, scientific discussion about space-time isn't fundamental, evolution by natural selection is not. No, I'm saying this presses important buttons that are very, very close to home. It's saying, you are not an object in space-time. So probably you thought you are an object in space-time. So I'm saying our best science says you are not an object in space-time, and your body, you are not your body, and that you might say, well, my neural activity creates my thoughts, and local realism is false. Neurons exist when they're perceived, otherwise they don't exist. Neurons could not possibly create your conscious experiences because neurons don't even exist when they're not perceived. I'm a cognitive neuroscientist. So I love to study the brain. I've participated in fMRI experiments, EEG experiments, and mathematical modeling of consciousness. I think we need more money for neuroscience, not less, because neurons are merely an interface description. They're not the truth. There is some deep, deep reality. And our little trivial projection of it is the 86 billion neurons and roughly the same number of glial cells that we see in what we call the brain. As complicated as the brain is, it's trivial compared to the reality outside of space-time. The brain is a mere interface projection of something far, far more complicated. So we're going to have to game up. We have to have much, much deeper theories. We looked in brains, we see billions of neurons. We thought, well, that's the complexity we're having to deal with. No, that's a trivial projection of a much greater complexity. So neurons don't even exist when they're not perceived. Neurons cause none of our behaviors. And the neural correlates of consciousness, well, people are trying to find what neural patterns, what neural areas and patterns of activity create our conscious experiences. The answer is none, because those neurons don't even exist when they're not perceived. Neurons appear in consciousness. They don't create consciousness. So,
Yes.
so this has all sorts of implications that people, so this is not just hand-wavy stuff. I'm saying this comes really close to home. I'm asking the question, who are you? And I'm saying probably every answer that you come up with is wrong. And you need to step back and say, who am I? And then sit in silence and be with who am I? And it's not comfortable.
Yeah, I as you see in the article that you shared on Entropy, I recently dove into Stephen Wolfram's approach, which, coming from a computer science background, I think is really helpful. And that's the way I've been viewing it recently, is tackling this problem of, infinite complexity. And then how do you modulate that data into data streams of, not too much complexity or chaos where it's unmanageable, and not too little where you don't make any progress. And so it seems like three-dimensional space plus time. So we have some hacks. We've got three-dimensional space where we can take out this information, this infinite complexity, and we can plot it out on this three-dimensional space. The stuff that's not as important, we put further out. The things that are really important, becomes manifest as this body that we're holding around, which kind of ties into Rupert Spira's dream analogy, is that, your consciousness, there's some part of it in the dream that is manifest as your dream. And it, if you take a substance in the dream, your dream changes, but it's not that that's actually happening in the dream. That's just a correlation to a deeper reality. So right. Three-dimensional space is one hack. And then also this dissociative or kind of recursive process of, okay, I am separate than all these other things. And even then, that's a little wonky, the way we define ourselves. Am I the cells that give myself cancer? Am I the one that's beating my heart? Alan Watts, goes into all that. But we have this idea of like other and self, because that helps us organize. And then we also, have this time, so we can iterate through it step by step. It's like dumping out a puzzle where, the first thing you do is you're going to separate the sky pieces. You're going to separate the pieces that match this. And you have to have some strategy for attacking this. And this is what you do in computer sciences, is have some algorithm. And recursive ones are particularly helpful because, you can have a method of attacking it. And then when it comes to the same problem within the chunk of data that it has, it does the same thing and subdivides. And then eventually you've got this multi-threaded process that has explored everything, comes back together to the final answer, which is very similar to what these spiritual traditions are talking about: reincarnation, mirror selves,
Mhm.
and yeah. So it's a many sense a data problem, data management problem, and so that's where the time is interesting. And I found it interesting. I read your paper on the Markov chains, and the one thing I found particularly interesting is the idea that a Markov chain is, to my understanding, a permutation of a system that doesn't matter how you got there, but it can take any of these paths into different permutations. And this concept of time, it is interesting because time, the past doesn't exist anywhere. It's not in physical space. It exists only in the sense that it's recorded in this space-time, physical stuff around us, our neurons. But there's multiple pasts because everybody is going to remember it differently. In the physical world, you can't fully reconstruct. So we do have some sense of the past that we've encoded into this eternal now, but it doesn't really exist. And the future also doesn't really exist. So it seems like your work on these Markov chains and decorated permutations kind of speak to this idea that time is this iterative process of trying out all these different permutations at different scopes of, and this is what psychology and healing and therapy is you're literally changing the past, and that it doesn't really matter how you got to where you are. You have a story that you tell yourself about, my teacher's parents treated me this way because of this, and this relationship ended this way. And then you go to therapy, and what actually heals is when you create a new narrative, like, oh, they treated me because their parents treated in this way, and that person treated me this way because of this relationship. So you don't actually change anything. You don't go in the past because it doesn't exist, but at the same time, you change your whole interpretation of the past. And so it's as good as any concept of time travel. So yeah, if you could speak to that idea of, only having this eternal now and this concept of time and maybe entropy. What are your thoughts on?
Yeah, no, I tweeted a link to your paper. I thought it was a very, very well-written paper and a lot
Thanks.
of good ideas. The Markov approach that we have is a model of a network of conscious agents interacting. So think about it as like a vast social network, like the Twitterverse, right? And a lot of people tweeting and following and retweeting and sharing tweets and so forth. So that's sort of, if you think about that, you're getting the right feel about what we're talking about. And you can then say, well, if this person tweets such and such a topic, what's the probability that follower will retweet it? You can ask, if so and so does this, what's the probability that this other person will retweet it? So you can ask these probabilities, and then you can see how information would flow through the whole Twitterverse, right? You can, by looking at those probabilities. So it's the Markov dynamics is really looking at how the tweets would flow through the Twitterverse and what would get retweeted, what would not get retweeted, and so forth. What would trend, what wouldn't trend. So that's sort of the top level, a feel for what we're trying to do. The Markov chains, you mentioned permutations. Permutations are an important subset of Markov chains. So if you look at the set of Markov chains on n states, 50 states or 100 states, whatever it might be, it turns out that there are n factorial permutations. N times n minus 1 times n minus 2 times n minus 3 dot 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 down to times 2 times 1. That's n factorial. But that's how many of the Markovian kernels relate to permutations. But there are n to the n Markovian vertices, extremal Markov kernels. Of course, there's an uncountable infinity of Markov kernels, but in terms of the vertices of what's called the Markov polytope, there are n factorial of them that are permutations, but n to the n of them that are Markov. So n to the n is much, much bigger than n factorial. So most Markov processes are not permutations. Most of them are not, but permutations are an important subgroup of them. And
So you're talking about like a geometric shape, and you're talking about the permutations, the faces or the sides, and then you're talking about the vertices as well.
Well, they're a subset of the vertices. So there's n to the n vertices on this big polytope. So if you have 50 states, like you can perceive millions of colors, but suppose you could only perceive 50 colors. We could ask, what is the set of Markov chains on, now I see red, now what's probably I'll see green and then purple and so forth, all these 50 colors. The number of vertices, the extreme Markov kernels, the Markov chains in this, is more vertices than there are particles in the known universe. And that's for just 50. You have hundreds of millions of perceptions. But when you get to 50, the Markovian dynamics of consciousness that we're proposing is unbelievably complicated. It's truly complicated. The permutations are big too. In fact, 50 factorial is a big number, but I don't think it's bigger than the number of particles in the known universe.
So what would the, to, I guess, extend this to our experience, like what would a permutation be in like a conscious experience?
Oh, well, a permutation, the standard notion of a permutation is like shuffling cards, right? If you have a deck of 52 cards, there are 52 times 51 times 50 times 49 times 48 times 47 dot 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 times 2 times 1 different ways that those cards could be arranged. And those are all the permutations of those cards. It turns out in particle physics, when they're looking at scattering of particles, the permutations and what they call decorated permutations are, to the surprise of the physicists, are turning out to be a critical structure outside of space-time, not inside space-time, but a structure beyond space-time that they can use to actually predict, for example, literally gluon scattering inside protons. It's truly, truly stunning. But so that's a whole other story. We can go into it, but I got into the decorated permutations because the physicists are using it for their scattering studies of scattering, like particle scattering at the Large Hadron Collider and so forth. But what I would say about the time and entropy issue, and we can go to the permutations more and scattering if you want, but the time and entropy which you talked about or asked me to talk about, this dynamics of Markov chains outside of space-time does not have to have increasing entropy. You can easily write down Markovian dynamical systems in which the entropy is not zero, but it doesn't increase. Technically, I'll put it this way: if the entropy at time n equals the entropy at time n plus 1 for the state, for all n, okay? But if you have such a Markov chain, it's a trivial theorem that if you look at the conditional entropy, so if I condition on some particular variable, so I say by conditional probability or something like that, then so I have a dynamics in which there is no arrow of time because there is no increasing entropy. So I've got some dynamics beyond space-time that's literally beyond time because there is no arrow of time, right? There is no increasing entropy. But if I take a projection of that dynamics, so I get a new dynamics, which is a projection of this deeper dynamics, but this new dynamics has lost some information, then the new dynamics will have increasing entropy because of the loss of information. And it will therefore have an arrow of time. So in our modeling of space-time, then, the idea will be this. There is a realm that we call this conscious agent dynamics that has no arrow of time. So there's no time. It's beyond space-time. It's beyond time. There is no arrow of time. It's dynamical, but atemporal in the sense that there's no increasing entropy. But if you take a projection of it that loses information, you get time not as an insight into the nature of the deeper dynamics, but as entirely an artifact of the loss of information in the projection. Now this then leads to a really interesting point. What I'm saying then is that from this framework, time, as we perceive it, is not at all an insight into any aspect of objective reality. It's entirely an artifact of the limitations of a projection. But time, if you think about evolutionary theory, going back to our earlier discussion, time is the fundamental limited resource in evolution. If I don't eat in time, I die. If I don't mate in time, I don't reproduce. If I don't get a drink of water in time, I die. Time is the fundamental limited resource. So I have praised evolutionary theory. It's a beautiful theory. I've published papers on it. It's an incredibly powerful theory. Now I'm going to say, as a hard-nosed scientist, all of evolutionary theory, notion of competition for limited resources in time, the whole structure of it, none of it is an insight into the nature of deeper reality outside of space-time. None of it. All of it is an artifact of projection. None of it will survive. That's the way scientific theories go. Your theory has a scope and it has a limit. The only question to each generation is, can you rise above your current theories? If you don't, you will look like a fool to scientists a century later, right? In 1890s, many scientists, many physicists were telling bright students not to go into physics because it was done. Newton had won, and we had our theory of everything. There were just a couple little minor problems. There was Michelson-Morley experiment about light. Speed of light didn't do things right, and there was black body radiation problem. But if you're really bright, you need to go into some other field because it's just mop-up time now. We look back and we laugh. All this wonderful, interesting stuff. And the same is true of our current science. Even to kid about us having a theory of everything is going to look foolish a century from now. Even kidding about it is going to look like they were so stupid to think that they were anywhere close. They didn't know about what we would say about the Newtonians. They had no idea about quantum theory. They had no idea about special relativity. They had no idea. They didn't know diddly compared to what we know now. And the same will be true a century from now. So for us to be talking about we're close to a theory of everything, if you don't want to be laughed by your great grandkids, just don't go there. Just admit right up front, we're doing the next baby step, and we're trying to figure out what's the limits of our current baby steps. So that's where entropy is. Entropy, time is an artifact of projection. It's not a deep insight into the nature of reality.
So I don't know are you familiar with Terence McKenna at all?
A little bit, yeah.
So he has I forget if it's novelty theory or novelty complexity or so he talked about, I guess it was kind of ridiculed, or he kind of predicted things in 2012. But I've listened to a little bit of his stuff, and it's very interesting because it ends up kind of coming to the same conclusion that I wrote about with time and entropy, is that there's this kind of play back and forth, going back to this idea of modulating infinite complexity, or just a higher order of complexity than our computational bounds, are the bandwidth constrictions that we have, is that we find this way to modulate it in. And then there's this kind of back and forth between adding more chaos, letting more in because we've sorted what we have. We've we've assigned it and figured it out and made some meaning out of it. Adding more chaos, kind of increasing entropy, and then again processing it. And this is, I think this is a pattern that happens through evolution, through individuals' lives. The entropy that a baby experiences very high because they don't have any order that they see in anything yet. Once they have constructs, once they know what the rabbit is, there's seemingly lower entropy because now there's order that they see.
Yep.
So, you have experience with meditation. Yeah. What are your thoughts on, and I think in your paper, I don't know if it relates to this idea of trace change. You talked about something like a lower order conscious agent being able to kind of downsample or try to represent a higher order conscious agent. And I've thought about this in terms of, even from the materialist perspective, the idea that our conscious experience is just some emergent phenomenon of these particles just being in a certain place. Even if you follow that faithfully, you find the door, you find the way out, because by that same idea, our cells should also be. It's very likely that they could be having conscious experience as well, because they have some passage, some information network exchange from the inside, the outside of the membrane between other cells, and then also zooming out. You're in a plane, you see humans or the whole earth, we're these little neurons passing goods, information, and certainly from your framework too, where space, time, these are all just kind of pointers or constructs to some deeper reality. So I guess if you could speak to simultaneous, again, this is speaking in the sense of time, but our cells or the information that we project in our VR headset as our cells, a conscious experience for them versus, humanity, human species, or the earth, or even these orders of conscious experience, hierarchical agents of consciousness, and the phenomena that we experience from de-identifying with Don or Gabe, a body, and zooming out and experiencing, people talking their mystical experiences of transcendence of space and time, or feeling societal pain or joy, or I think the other end of the spectrum too, just experiencing a cell or a inanimate object.
Well, saying that space and time are doomed, so that they're not fundamental, has an important implication. It means that reductionism is also doomed. And reductionism is the idea that if you start with smaller and smaller objects in space and time, you find more and more basic elements of reality and more basic laws about how they interact and operate. So you're finding deeper and deeper levels of truth. But space-time is doomed. It's not fundamental. So reductionism is not fundamental. It doesn't work. So when I look at my mathematical model of consciousness, I'm not trying to boot up consciousness from some kind of mathematical operations by any means. So my attitude is very, very different from most of my colleagues. Most of my colleagues are trying to figure out how, if you have a physical system that's not conscious, but has the right kind of complexity, that then consciousness will emerge. That's what they're trying to do. And that 99% of the theories of consciousness that my friends and colleagues, who are, they're brilliant and they're good friends, they're all in that kind of, they're reductionist or functionalist kinds of theories. They're trying to show how non-conscious substrate, typically physical substrate, can give rise to consciousness if it has the right kind of near chaotic behavior, whatever kind of complexity that will give rise to the magic of consciousness. Now, the question, if someone proposes such a theory to you, here's the question to ask them, and it's a showstopper. Just ask them, great. So you have your theory of consciousness, like integrated information theory or orchestrated collapse of neural microtubules or global workspace theory. So you have a theory of consciousness. So here's the question: what specific conscious experience has your theory explained? Like the taste of vanilla or the smell of a rose. What is there any specific conscious experience that your theory says this must be the so-called Q shape, the pattern of integrated information that must be the taste of vanilla? It couldn't be otherwise. And the answer will be, well, we can't give you none. Nothing. There's literally nothing on the table. They've drawn a complete zero in terms of specific. Now, what they'll say is that but we can give you a rule for or a way of finding what systems are conscious and which ones are not. Which neural systems are. To which I reply, space-time is not fundamental. It's just a headset. The distinction that we make between living and non-living things is not principled. It's an artifact of the limits of our headset. The distinction we make between conscious and unconscious things is not principled. If your theory says these parts of space-time are conscious and these parts are not, your theory is wrong because it's not possible. It's very much like here we are on Riverside. We're talking to each other. I see pixels, some pixels of Gabe's face, but some pixels of Gabe's sweatshirt and of the wall and of the room behind you. So now I might say, well, look, the pixels that are of those pixels of Gabe's face, those are the conscious pixels, and the pixels of the wall behind him, those are the unconscious pixels. Well, that's an unbelievably dumb mistake. Pixels are just pixels. Some pixels give me insight into what Gabe is thinking and feeling, into the consciousness of Gabe, and other pixels of the wall do not. But pixels are just pixels. There's nothing special about the Gabe pixels over the other pixels. When you understand that space-time is a headset, it's just a data structure, then the distinction between living and non-living and conscious and unconscious is as smart and as intelligent as distinguishing between the conscious pixels on my screen and the unconscious pixels. It makes no sense whatsoever. It completely misunderstands what our best science is telling us. Space-time is not fundamental reality. It's a trivial data structure, period. It's like the screen on your desktop, period. So most of the models of consciousness, from automata, interacting automata and so forth, what they're trying to do is to start with something that's not conscious and put it in the right kinds of chaotic or near chaotic situations, or the right kind of complexity, so that somehow consciousness will be created. And again, to those theories, I say, tell me one specific conscious experience that you can create. I want no hand wave. What specific conscious experience? What states of your model must be the taste of cinnamon and could not be the taste of vanilla? Please give me. I'm a scientist here. I want hard-nosed results. What are your results? What specific conscious? None? Well, then maybe I better spend my time somewhere else where we actually can get theories that make predictions that are interesting, instead of no predictions at all, or false predictions that these pixels are conscious and those pixels are not. Why should I take that theory to be that's actually dangerous now, because if you bring that into the hospital and you're trying to make decisions about life and death, when you have a pixel theory of consciousness, that's actually scary. So you can see that the stuff might sound airy-fairy and out there, but it has really important consequences. I'm predicting that no theory of these kinds will ever get a specific conscious experience. They in principle cannot explain any conscious experiences. They will be shown to be failures. And not because these people are dumb, they're brilliant. Most of them are my friends and colleagues. I know these people. They're absolutely brilliant. And I understand why they're going after the reductionist framework. It's worked so well in the history of science. But what we've learned in the last 20 or 30 years in physics, and now in evolutionary theory as well, is that space-time had a good run, and it's over. It's no longer an adequate framework. It's time to get past space-time, and physicists are doing that. In the last 10 years, they found the new structures entirely outside of space-time. The amplituhedron, certain associahedra, cosmological polytopes. They're finding, and the decorated permutations, they're finding these structures not curled up inside space-time, not little entities inside space-time, utterly outside space-time, and outside, by the way, outside quantum theory. So quantum theory itself is not fundamental. My own take, and I agree with some physicists like Nima Hamed who also say this, is that space-time will emerge from something deeper with space-time. I'm sorry, quantum theory will emerge with space-time. Quantum theory and space-time together will emerge from deeper structures.
Have you read Wolfram's kind of integration of thermodynamics and quantum physics and relativity and space-time? He's talking about this. It's this.
Yes. Yes. And I think he's got a lot of interesting mathematical ideas there. He's brilliant. If we're trying to boot up consciousness from that, if the goal is to ultimately boot up consciousness from unconscious ingredients, that's doomed to fail. That can't work. But if you're trying to use that as a dynamical model for the structure of space-time, for example, that's perfectly fine. So I'm all for it. But I should say something about my, someone might say, well, you got this Markovian dynamics of conscious agents. It's like a network of interacting. Aren't you doing a reductionist kind of thing as well, right? Are you? And I'm not. My attitude is very, very different. I'm not saying there are these unconscious things, but if you get a network of them together, consciousness will emerge. I'm capitulating at the very start. I'm saying consciousness is fundamental. That's my assumption. I'm not assuming that unconscious things are fundamental. I'm assuming that conscious experiences are fundamental. And I'm using mathematics to model that assumption. And what I'm going to then do, and by the way, I already know that even my mathematics it does have a scope, but it has clear limits. I cannot model, we talked about perhaps there's this unified consciousness, some one consciousness, right? And I think that that's probably right. My mathematics cannot model that. It simply cannot. And I take that as a clear limitation of the mathematics that I'm working on right now. It's provably the case that my Markovian dynamical system cannot concretely model a unified single conscious agent that gives rise to all the little conscious agents. So I know from the get-go that what I'm doing is not the final theory of everything by a long shot, but infinitely far from the final theory of everything. So it's not trying to be modest in some weird way. It's literally the case that I'm just taking a baby step into a theory of consciousness. So this is not false modesty. It's just the math is in my face and it's rubbing my nose in it. Don, you're nowhere near a theory of one consciousness, and there are principal reasons for it. So I'm not trying to boot up consciousness from some other substrate in some mathematics. I'm just saying.
It sounds like in your model, and maybe this is I've listened to your headset model, which I think is really helpful, but it seems like one limitation of that is that it doesn't have this kind of hierarchical or fractal nesting, because you can take the headset off, but you also, there's not an analog to like a team taking its headset off. But I imagine that your model allows for, there's some way to slice it where this would represent the conscious experience of a smaller order that, a neuron maybe doesn't exist except through our headset, but there's some information that we're mapping onto that structure.
That's exactly right. So it's easy to prove that these networks of conscious agents, they're Markovian nets, are computationally universal. So anything that you can build or compute with neural nets, you can compute with these conscious agent networks. So, and we've seen with ChatGPT and so forth that you can do a lot of interesting things with neural networks. So all that stuff you can do and more, because the Markovian networks are not limited to computation. There are interesting technical reasons why they're not limited to Turing computation. So ultimately, the notion of the headset and the interface, I would love to build these networks of conscious agents that actually build a space-time headset. That's one of my goals, is to actually show how that's done. And then what I want to do is to take that dynamical system and have it. Headsets are for looking at things. So I'm going to have it start looking at this network of conscious agents, and in particular, look at the part of the network that built the headset. Right. So I'm going to have a network of conscious agents that's building a headset, and then turn that headset and have it look at the conscious agents that are building it. What will I see? It will probably look like neurons and brains. So in other words, a neuron, the brain, is what we see when we take our headset and turn it on to the network of conscious agents that's building the headset. And that's why I'm saying neuroscience is going to be far more complicated and needs far more funding, because that network is going to be much, much more complicated than the 86 billion neurons that are the trivial projection in the headset of something far deeper. And so, by the way, I'm not going to be modeling the human brain anytime. And so maybe a little, a gnat brain or something like that. So
that's fascinating. I mean, it's similar to what Bernardo Kastrup talks about. A brain is what another avatar looks like.
Exactly. That's right. It's not the truth. It's just a view. So, but I would say the big bottom line on all this, because we're getting near the end, is almost every theory of consciousness that you'll see is assuming non-conscious starting point. My basic ingredients are not conscious, but if they have the right kind of complex interactions, then consciousness will emerge. And in every case, just ask them, what specific conscious experience have you gotten to emerge? Can you get vanilla? Can you get the smell of chocolate? Can you get the sound of a trumpet? And sometimes I've had to ask. I've been on stage with Stuart Hameroff, good friend. I love Stuart. We're good friends. But on stage, hey, science is science. And I remember one time we had 500 people in the audience, and I said, Stuart, so what specific orchestrated collapse of quantum states of neuronal microtubules must be the taste of chocolate or vanilla, or whatever conscious? Can you give me one, Stuart? Can you give me one? And I had asked the question 6 or 7 times over about 3 or 4 minutes before he finally said, I can't give you one. And he knows I'm going to do that again. And I'm going to do it to each one of these. At some point, these guys are brilliant. They need to stop trying to do something that's impossible. It's impossible to boot up consciousness from unconscious ingredients. Cannot be done. The sooner you recognize that, then we can unleash their talents where they can be used. How can we use a theory of consciousness to show how space-time emerges? That we can do. And we need brilliant minds to work on that problem. So, and I'll just say this one last thing. Their theories stipulate space and time. They say, grant me space and time and objects in space, like neurons or particles. And then we're trying to explain consciousness, but we can't. They can't explain any specific conscious experience. So they're having to stipulate the conscious experiences. If they believe in conscious experience, they're being stipulated because they're not being explained. So here we have them stipulating space and time, physical objects in space and time, and stipulating conscious experiences as well, because they can't explain them. So my attitude is, well, I'm only stipulating the conscious experiences. So by Occam's razor, the fewer assumptions, by Occam's razor, that approach wins, because if I can only stipulate conscious experience and then explain space and time and all the so-called unconscious behaviors inside space and time, I don't have to stipulate them. I can explain them. And so that theory then has more explanatory power, than the physicalist theory, which doesn't explain physicalism, it assumes it, and it doesn't explain consciousness, it has to stipulate it. So why don't we go where we can actually get explanatory power? I'm hoping my colleagues are brilliant. My goal in life is to get them on this track, and then I won't be able to keep up because they'll run circles around me.
Yeah. Well, thank you so much for coming on, and thank you. I mean, personally, having people like you who have, yeah, taken a position that I'm I'm sure you've gotten a lot of pushback and probably was difficult to start. I appreciate seeing other people. I mean, that for me, that was the most difficult when you come to insights, whether you're leaving a religion, whether you're leaving a model of reality, when you have to let go of everything that you've had to make meaning, it's scary and difficult. And so seeing other people that have pioneered that way and maybe don't have all the answers, but they say, hey, there is something in this direction, something better than where we came from, is, yeah, really helpful. And so I appreciate your work and your podcasts and collaborations with people.
Well, thank you, Gabe. I appreciate it. And thanks for this kind invitation. And maybe that's our point in life is exploration. Or maybe the
Yeah.
big question to explore is who am I? That
Yeah.
might be the big
Exploration
question.
and I think collaboration and, reading, I read Sapiens because that kind of becomes sort of
Yes.
the atheist Bible for a lot of people, at least coming out of religion or Mormonism, it seems.
Right.
But it's interesting, even though that's from a fairly materialist perspective, it still has these themes of like unity and everything's
Yes.
moving towards unity, and there's the individual, but there's also these concepts of like LLCs and corporations and the species
Right.
itself and corn as an entity domesticating humans.
Right. Right.
So
Yeah. Right.
it's got all the roads, I think, lead to the same direction. Some are more difficult, and others are more efficient. And so I appreciate your work.
Thank you very much. Thank you very much, Gabe. It was great to talk.
Thanks.
Okay. Take care.